Righty. Down toward the end here, everybody. It's hard to believe, but we are almost done. Today I want to pick up where we left off and finish that up fairly quickly and get on to some distributed networking with respect to storage. So if you remember last time, we were talking about network layering. And the way I like to think about the point of network layering is you're taking physical reality and turning it into a much better abstraction. So, packets are limited size. That's the maximum transfer unit, 200 to 1,500 bytes. Get an arbitrary size communication. We go from unordered packets to ordered, unreliable to reliable, machine to machine, into process, etc., insecure into secure. So this is kind of the point of the layering, and we were doing a very quick run-through of the layering last time. Just to remind you, we talked about the IPv4 packet format that looks like this, and it's got many interesting things in the header, which you would talk about in 168. But the important parts that I wanted to mention is the protocol field here is 8 bits, and that's what distinguishes between TCP/IP and UDP and ICMP, etc. And fundamentally, what we talked about last time is the datagram, the IP datagram, which routes a packet from here to an arbitrary other point in the public IP network and using this header, okay? And so this header is standardized across the world, and that's kind of why that's why IP has taken off so well. As you are well aware, probably, there's also an IPv6, which is a little slower to get adaptation. And there's a way to wrap IPv6 in IPv4 packets as well, which is kind of the way it's often done. So at the very end of last time, we were talking about the transport level. We kind of talked about physical data link, network, and transport. Two things that are of interest here at the transport level, which is setting that protocol, among other things, is UDP, which is kind of a no-frills, best effort IP, and TCP, which we didn't get to talk about much. So transport layer adds semantics to the IP datagram network. So in the case of UDP, what the semantics are is it's from process to process rather than from machine to machine. TCP has a lot of other more interesting semantics, like retransmitting lost packets, ordered delivery, flow control, congestion control, all of those interesting things. And I'm very quickly going to say something about that as well. But so UDP is protocol 17, TCP is protocol 6. I don't expect you to remember the protocol numbers. There's a bunch of other possible transport protocols. There's many. Just do a Wikipedia search on IP transport protocols and you'll find them. Things that the transport protocols typically don't provide are things like delay or bandwidth guarantees, sessions that survive when your IP address changes, security, denial of service, resilience. Those things are not typically provided by the transport protocol. And in some cases, some of these things like denial of service actually need to be provided by some of the intermediate networking layers, which is, of course, a violation of the end-to-end philosophy. So I pointed this out last time, UDP. This is a great example of what typically happens with an internet protocol is you take an IP header and you wrap more header on it. So the header that you add with UDP is really pretty simple. It's just 16 bytes. It's got 2 source ports and a length and a checksum. And so you start with that 20 bytes I showed you earlier. You add this extra stuff, and now you got data. What do you get out of that? Well, you get ports. So just by adding a little bit of extra data, now suddenly we can talk from a process to a process rather than from a node to a node. Okay? And so the ports are really going to allow us to demultiplex. The important aspect of UDP is low overhead, and it's often used for high bandwidth video streams. You can use UDP in a very antisocial way if you're not careful. And so it doesn't back off automatically if nodes in the middle are overloaded. Okay, so let's now pop up. So I'm going to talk more about how TCP achieves some semantics in a moment. But let's pop up the last layer to get this little walk through the layers over. We're going to talk about the application layer, which is 7, not 5. we're in a funny scenario where I would say the Internet Protocol was a default standard. The OSI protocol was a, negotiated standard, and the default one won. Okay, and so what OSI calls session, presentation, and application layers are really just kind of lumped together into the application layer. So basically that layer provides any service you want. The interface depends on the application. The protocol depends on the application. Lots of examples. Okay, pretty much anything you can think of that communicates over the internet is an application layer protocol. You might say, what happened to layers 5 and 6? Well, they're kind of swallowed by the application layer. So, for instance, also on Wikipedia, I'm giving you things you can look up. You can find out the fact that, for instance, RPC is kind of considered a session layer protocol. Sometimes sockets are. Encoding is a presentation mechanism to deal with different sides. XDR, which is the standardization portion of Sun RPC, which allows you to communicate between different endiannesses and so on. That's also considered a presentation mechanism. Okay. Good. Yes? No, that's a protocol for doing cloud computing type stuff. Okay, not the game. So, okay, so here we got it all. Now, what's interesting, again, I'm just going to point this out, is you start at the application layer with your data, you wrap transport header on it, then you wrap a network header on it. So this is basically like the TCP header. This might be the IP header. Then you wrap the Ethernet header if you're going to communicate over Ethernet. And then you turn it into high and low bits or whatever, and it goes across. And then you undo it at the other side. And so typically, depending on how many layers you got, you keep adding headers. And it can get quite long, especially since at the network layer, you can have IP in IP encapsulation. So you can build a VPN network which takes your IP packets, wraps them with different IP packets, sends them over a link, and unwraps them to do a local IP network. That's a way sometimes you get VPNs that look like they're connected directly even though they go over the network. And you can, of course, wrap that as many times as you want. So the headers can grow arbitrarily and without bound. Okay, which gets you in trouble with the MTU sometimes. If you try to have too many headers wrapped and you try to go over a low MTU link, you might run into a mess, and that does happen. Okay. So 5 layers, lower 3 are implemented pretty much everywhere. Top 2 are implemented at hosts. Okay. Logically, the layers interact with their peers in the corresponding layer. You could say that the IP narrow waist is about standardization of IP networking across the world. End-to-end arguments are typically about application-to-application communication. Okay? Everybody with me on that? Now, the interesting thing for me is you can talk about this abstract idea of communication across protocols, across layers, and so on. But what's more interesting is kind of the physical communication. So what happens is, at the source, things go down, and then they go across through one or more routers, which typically come in the physical link, go up to the network layer for routing, and then come back down again, and so on. You do that a bunch of times, and eventually you get to the other side. Okay? So this is kind of what happens to the actual packet. So clearly, this communication is virtual in some sense because it really happens because this packet eventually gets unwrapped at the other side, and you got a communication between the two. But it isn't like there's a direct link through all the routers out there, or there. I guess that's a philosophy question if you want. Okay. Now, the other thing that's kind of interesting is if you were to now peer inside, say, the Linux kernel, this is an embedded TCP/IP stack from an embedded TCP/IP stack paper. But what's interesting about this is the implementation of things like the network drivers and so on are a little different from the other device drivers because they have lots of stuff that's about starting and stopping streams and packets of information. Okay, and so if you have your unique network hardware here, you're going to write a network driver that has to deal with some of these interfaces, like starting a transmission and receiving an interrupt for a packet coming in, okay, and opening the network and so on. And then the protocol stack is the part just above that does things like retransmits packets for TCP/IP and so on, okay? And then, of course, there's the user interfaces and parts of the socket library up above and parts of it in the kernel mode and so on. So really, we look at this, we say, oh, yeah, the packet flow goes up and down. Well, it's going in the interface, up, possibly through parts of this in the router, and then back down and out again, and that's kind of how a router works. Okay? Now, one of the things I did want to point out as a unique detail about networking, just for those of you that might get into this for interest, in the network layers of most kernels, what happens when a packet comes in is it's put into a whole set of these socket buffers that are linked together. And so one packet might have a bunch of these buffers linked together that you can take data out of and put data into. And the reason they do it this way seems messy at first, but when you receive a packet, which is this top-level thing, you can ask that packet to pop off the top header, like the one from the Ethernet, so that you can look at it, and then the packet gets automatically shrunk to not have that header on it, so that you don't have to you don't have to copy bytes anywhere. And so the network stack, when the data comes in, you pop off the Ethernet header by just asking this structure to do that, and you process the Ethernet header, and then you pop off the IP header and then the TCP header, and you could do that without actually copying any data around. And it's only when the data actually has to go into the user or out of the user that you end up copying stuff. And so the complexity of this buffering scheme, which you'll run into in pretty much any networking implementation you run into, is all about making the addition and deletion of headers happen efficiently without copying. And that's because otherwise you're basically copying packets around all over the place, and it gets really slow. All right. The other thing I wanted to point out is there's a lot of optimizations to deal with the fact that our networks are extremely fast. So for instance, what's interesting is if you have an application that's about to send some data out, the real path of that is typically either it goes into the TCP implementation, for instance, or the TCP implementation can pass it all the way down through Ethernet transmit and so on, depending on whether it's ready to transmit that data directly to the network or not. Okay, and then on the input side, that's kind of interesting because, for instance, there's timer hardware which wakes up every now and then and asks TCP, oh, gee, do we need to retransmit something or not? And when that happens, it causes a retransmission. Okay? And this particular thing, which was called the new API, decade ago, is when a packet comes in, it raises an interrupt, which then is transferred into a soft interrupt in software. So all of this structure is about making sure the interrupts, the hardware interrupts, don't stay disabled very long. And that software interrupt then goes all the way up into the TCP stack and potentially pull everything out of the buffer without any further interrupts, and then re-enables interrupts. I mentioned that kind of really early in the term as a way of dealing with the fact that this network might be a 40 gigabit network, and how do you deal with that with all these interrupts? Well, you try to take an interrupt on the first packet and then just empty the thing out for the rest of them. Okay? And so this is kind of another way of looking at how that happens. The interrupt happens, you interrupt the user program, the hardware interrupt happens, goes into the device driver, schedules a software interrupt, and then that software interrupt does a bunch of stuff, but the software interrupt's at lower priority than all the hardware ones, and therefore any high priority hardware interrupts can still go, but meanwhile we're emptying the packets out of the hardware, and then eventually we return from that software interrupt and execution keeps going. Okay? And I just wanted to give you a flavor for that because I mentioned it really early in the term, and I wanted to remind you a little bit of these kind of optimizations that try to make sure that you're not doing too many hardware interrupts because they can be expensive. Okay, I'm going to pause here for a second and see if anybody has any questions on this. Just giving you flavor, yeah. Can you explain what a soft interrupt is? Yeah, so a software interrupt is basically a situation where the kernel sets a bit in the interrupt controller that says cause an interrupt, instead of the network card raises a line that says I've got an interrupt. In the case where the network card raises a line, typically what happens, if you go back and look at my interrupt controller slides from early in the term, is you disable all the interrupts, you process the network interrupt, and then you re-enable stuff. A software interrupt, since I've set it by the kernel, I've turned that bit on, it's lower priority than all the hardware ones. And so I can actually have the software interrupts disabled while the hardware ones are continuing to come in. But a software interrupt will interrupt user code. So the user code isn't running, but all the other interrupts can run. And so it's a way of organizing this kind of structure so that it's very easy for the kernel to request it gets interrupted in a controlled way and then let all the asynchronous interrupts happen still under the covers. Okay, I realize that's a pretty short description, but that's pretty much what happens. And so basically software interrupts is one that the kernel can ask for in the interrupt controller. And there's often, like if you were to look at the Linux kernel, there's a bunch of different schedulers that can decide if there's more than one software interrupt going, which one gets to run, and so on. But that's kind of at the level, higher level than the low-level hardware interrupts. So, all right? Good. So now I want to start down this, finish up TCP/IP by asking a little bit about reliable message delivery, because we're going to want that for the distributed storage we're about to talk about. So all physical networks can garble or drop packets. Physical media may not transmit. It may run into a collision. When you transmit close to the maximum rate, you may get more throughput but lose some packets. Maybe you're running your network connection at a very low power, just on the edge, so that you get really good power efficiency, but you're also losing bits. The other way to lose, so that's a direct loss of bits on a connection. The other way, which people often don't think of, is another way to lose packets is congestion. Too many packets are all coming into the same part of the system. What do? You can't just take them all, because you might run out of memory. And it might not be fair if you've got one connection that can spit packets out really rapidly and another one which is really slow. It may be that the slow one never ever gets to send anything. So these are congestion issues you need to deal with. And roughly speaking, congestion is a situation where there's no place to put the incoming packet. There might be insufficient queuing at the router or switch. If it's a broadcast link, you got overlap with two communications and so on. And so we want to try to deal with both physical media loss and packet loss due to congestion. Okay? What is a router to do when it gets too many packets? It starts dropping them. Okay? And that's going to cause retransmissions, which could cause all sorts of mess if somebody just keeps retransmitting like crazy and the router just keeps dropping it. Basically, we're wasting a lot of bandwidth and power to do nothing. And so it'd be nice to not do that. Okay? So reliable message delivery on top of unreliable packets is the general goal. And we want to make sure that the packets make it to the receiver. If you remember that little stack diagram I showed you where the applications go all the way down and through a bunch of hops and come up on the other side, we'd like that to actually work. So the packets actually do make it, despite the fact that there's congestion. And in particular, we'd like every packet received at least once and every packet received at most once. How do we do that? And we could combine it with ordering. Wouldn't it be nice if when I sent packets 1, 2, 3, that they show up on the other side 1, 2, 3? So these are kind of what we'd like to get out of our TCP protocol. And we could start with the question of how we ensure transmission to work. And the answer is, well, we could use acknowledgments or ACKs, right? So the way you detect garbling at the receiver is, say there's a checksum over the packet, so the packet shows up, and either it doesn't show, the packet's transmitted. If it shows up without garbling, you get an ACK. If it doesn't show up, or it's screwed up at the other side, you don't get an ACK. Okay, so what do? Well, you get a timeout. So when you don't get an ACK in a short enough period of time, you retransmit. Simple idea. What are some downsides here? Well, it could be that I didn't get the ACK because the ACK was lost, not because the packet was lost. And so this simple idea could very easily set up a situation where the receiver gets multiple copies of the same data. And obviously, if I only want one copy of the data, that might be an issue. So if the sender doesn't get an ACK, does that mean the receiver didn't get the original message? No, could have gotten duplicates. What if the ACK is dropped or the message gets delayed? Well, we retransmit. And so once we start retransmitting, we're now in a situation where we could easily violate the don't get more than one copy of a message problem. Okay? Everybody with me? So far, so good? Now, so ACKs sound good enough, but how do we deal with this duplication problem? And the solution is maybe you put a sequence number in the message to identify when we're retransmitting. So wouldn't it be nice if B did get 2 copies of the packet, that it knew it was 2 copies of the packet? Well, you got to put a number in it to say this is packet 1, this is packet 2, packet 3, right? So, well, what are our requirements for this sequence number? Well, the sender has to keep a copy of unacked messages so it can retransmit, and the receiver keeps track of all possible duplicate messages so it can throw them out. So we have to have queuing at one side and tracking at the other side. And, well, here's one. We have a very single bit in the packet header, okay, called the alternating bit protocol, and you send one message at a time. And what happens is the first message has the header bit of a 0, and the second has a header bit of a 1. And the reason we have that distinction is that way I know I'm sending bit 0 until I get an ACK on 0, and then I send bit 1 until I get an ACK on 1, and the receiver can look at the bit and decide whether it's a duplicate or not, because if it sees 2 zeros in a row, it figures it's probably got duplication. Now, how many people like this protocol? Okay, a couple of you. Any reasons we might not want to like this protocol? Yeah. What if we skipped one? Well, clearly this doesn't allow you to skip one. I'm assuming some stream of packets that all have to go to the other side. Yeah.
What if, like, you were loading a website and you had, like, resources from different places? You have to, like you wanted to send multiple different files at the same time. You have to wait for each file.
Yeah, it's more the second one. So the real issue here is the way you get performance out of the network. And remember, we were talking about communicating with Beijing a lot last time. For whatever reason, it was stuck in my head. But the path from here to there is far, and there are many routers in between. And if I only have one message going at a time, it's going to be really slow because the message is going to go all the way over and there's going to be an ACK. And then the message is going to go all the way over and there's going to be an ACK. And so in order to get good performance, we're going to need to have more than one message at once. And this completely fails when there's more than one message in transit. Okay? And so pros are simple and small overhead. Cons, we'd like to fill up the wire. We'd like to have wire latency times throughput packets in flight. And we just can't do that with this. Okay? So, and it also, by the way, doesn't work if the network can delay or duplicate messages arbitrarily. So think about this a second. I send packet 0. It doesn't show up. I send packet 0 again, I get an ACK. Oh, that's good. And I keep going. The problem is the reason packet 0 the first time didn't show up is it got delayed because it's taking an around-the-world trip on some big loop in the network and eventually comes back and it gets delivered twice. But only after a very long time, right? If that happens, I can't suppress it. Okay, so clearly nobody does it this way. The better thing we could do is some sort of windowing thing. This is not really TCP/IP yet. But the idea here is send up to n packets, so we have enough bits, log n bits, to have up to n packets. Here's n equal 5, let's say. There's a queue at the other side, so I know that if n is 5, my queue can hold at least 5 things at the other side. And for each thing that comes in, I get an ACK, and then I can reuse that sequence number when it finally comes in. Okay? And what's good about this is the ACK really says received all packets up to a certain sequence number if I wanted to. And it sort of tells me that, well, packet 0 definitely got in. And so the dual purpose of these acts is reliability, confirming which packet was received, and ordering. So if I label my packet 0, 1, 2, 3, 4, when they show up, even if they show up out of order, the queue can reorder them. Okay? So sequence numbers seem useful for us. So what if the packet gets garbled or dropped, sender times out waiting for a particular ACK, and I resend just that missing packet? Okay? Now, should the receiver discard packets that arrive out of order? That's a question. The answer is, well, it's up to you. There seems like there's no good reason to throw out packets that are out of order, because if I allow myself to hold on to the packets out of order, then, I'm just waiting for the one missing packet. And so it would be nice if packets arrive out of order that I order them at the queue and I don't give them up to the software until things before them show up, but there's no reason to necessarily throw them out if I have enough queue space. All right. So what if the ACK is garbled or dropped? Timeout, resend. Okay, so this is a fairly simple scheme. Are there any questions on this? Because this is kind of the inspiration for TCP. Now notice I'm labeling every packet with a sequence number. TCP is going to be a little trickier, and I'll tell you how in a moment. But okay, so I want to give some administrivia. So last midterm is a week from today. Hard to believe. You can have 3 handwritten sheets of notes, both sides. I'm going to focus on material from lectures 17 to 24, but all topics are fair game. I don't know if you were tracking this or not. When we asked for conflicts, originally we said, anybody have conflicts between 5 and 9? So it turns out that our midterm time is 5 to 7. We've got rooms for it. If you've got a new conflict for some reason, although we were, I think we asked for conflicts from 5 to 9 originally, let us know right away. But we will be doing that. It's a little earlier. You get to go home earlier and I don't know, relax. So watch Piazza for room assignments. One of the good things about doing 5 to 7 next Thursday is roughly half of you guys will be in here for whatever that's worth. We won't have a little dinky room like we did in Evans. Who all got to be in the little tiny room in Evans last time? A few of you. Wasn't that exciting? Come to class on Tuesday, please, because HKN will be here, and we'll also talk about some cool security things as well. And don't forget to do your group evaluations, even for Project 3. You know what? The other thing I forgot to say in this administrivia is I'm going to be doing a final lecture on Tuesday in RRR week. So it'll be on, not on the midterm, because it'll be after the midterm, but topics you might be interested in, let us know. I don't know if William has put out a Piazza poll or whatever for topics, but if he hasn't, send them to me directly, whatever, and I will pick the top few of them and talk about them. So whatever you'd like to hear. Okay? Presumably something to do with the class, but it doesn't always have to do with the class. Probably not politics. I think I said that last time. Get myself in trouble. I could just see the Daily Cal now. Berkeley professor goes off on, anyway. Tangent. Goes off on a tangent. Yeah, that's what I meant. Questions? So what does TCP actually do? So TCP is the transmission control protocol, okay, or the totally cool protocol, I guess. Basically, the idea is you have a stream of bytes in and a stream of bytes out. And the point is the bytes come out in the same order they went in. And they also, if they go in, they come out. So it's a deliver once and once only protocol. So notice how A has made it out over here and S is just about to get in. And so it's IP protocol 6, and there are, this is pretty much what you use when you use the web or whatever, okay? And when you've been opening sockets, and experimenting with that kind of stuff, you're basically probably doing TCP unless you explicitly ask for UDP. Okay? So details. So this is where it's a little different from our little simple protocol last time that I mentioned a couple of slides ago. So it takes this byte stream and it chops it up into pieces, okay, based on timing and whatever. It doesn't really matter, but it takes a slice and it hands the slices to IP, and IP may chop it up further based on MTUs being too small or other circumstances. And it uses a window-based acknowledgement protocol, but the window reflects bytes at the receiver, and the ACKs that are coming back and the sequence numbers are what position are you in the byte stream, not what packet are you on. So if you were to chop this up into more pieces and send it over, it wouldn't change the assignment of a sequence number to a particular letter. That will still be the same no matter how you chop it up. Okay? And I'll show you an example of this in a moment. Okay. And lost packets are retransmitted. So the API here is very simple, and I don't want to hover on it too much, but it really is. You send some bits in one side, and they show up on the other side, and that's it. That's what it does. Okay, so it's very clean. It may take a long time, or they may get delayed if parts in the middle go down, and if they go down for too long, you might actually totally lose the connection. But the idea is basically the bytes go in and the bytes come out. And the key thing also about TCP is a good citizen protocol. And so this router here might have 12 million different TCP streams going into it, in which case the protocol will adapt to make sure that everybody gets their fair share. Now, in the case of 12 million simultaneous streams, probably everybody's fair share is going to annoy them because it's not going to be very much, right? But unlike UDP, which we just talked about, where it's possible to shove so much in to a stream that you can kind of cut out other people. Okay, it's much harder to do that with TCP. Questions? I'll make sure we understand this API here before we do anything with it. This is totally familiar to everybody, I hope? Yeah. And by the way, question? No? Yeah. So UDP can be used to overload the network in some instances. What a lot of routers today in the middle do is they will recognize the stream as being a bad citizen and may even cut you way back or cut you off. But in principle, barring stuff in the middle, with UDP, there's no control because it's a one-sided protocol, send. TCP, because it's got ACKs, can adapt the rate that it's injecting things to. Basically, what you want is you want the rate that the data is going in to match the slowest link or router in the path. Yeah.
Just to make sure, what do you mean by window? That's like the thing that we saw a few slides ago, where you send like 4 of them with the sequence number from.
Yeah. So, in fact, the window, I'm going to show you much clearer what the window is in a second. But the window represents how much, there's a couple of windows, how much data can be in transit and how much data can be received at any given time. So there's 2 windows. And by the way, the reason we want a lot of things in transit is basically to optimize this link, because we cannot get the full bandwidth that's available to us unless we've got a lot of things in flight at once. That's the way we have to optimize. So you've got to have parts of that stream have got to be going all at once. And so you want to make sure the window is big enough that you can fill this up. And on the other hand, the window of things you're transmitting can't be too big. It's got to match a buffer at the other side, because if your window of things are too big and the receiver gets slowed down, then all these bytes could slam into the poor application at the other side and get lost. And that's not something we want to have happen. Okay? Good. So the window at the receiver side is got to be bigger than the total window of what we're sending. Okay. So what does this mean? So the sequence numbers are basically you could think of the sequence numbers as representing all the possible bytes that could be sent. And early sequence numbers represent things that were sent and ACKed at the receive side. There's a window here of things that have been sent but not acknowledged. And then there's, of course, the things that haven't been sent yet. Okay? And then on the receiver side, you've got sequence numbers that have been received and given to the application. You have ones that have been received and buffered but not given to the application, and then you've got ones that are received. But this sequence number string, the sequence numbers start at a given point, which is not 0. It's a random point when you do your connection, and then they grow by 1 for every byte that goes across. Okay? Questions? All right. Now, clearly, by the way, the size of the number of things we're allowed to be sent but not ACKed should not be bigger than our total buffer space that we happen to have at the receiver side. Yes?
How does the sender adjust the window?
I'll show you. The sender adjusts the window based on information that's actually in the TCP header coming back from the other side. Okay, here's our window. So this window represents the receiver's window. Okay, starting at sequence number 100. And just to be clear, when we set up our original connection, we get back an ACK from the other side that says my current sequence number that I've received up to is 100, and my window size is 300. That's what's coming back on the ACK in the header. Okay, and by the way, since TCP is a bidirectional protocol, packets that are giving me an ACK from my outgoing communication can also be giving me incoming communication of data, okay, and vice versa. So TCP is bidirectional. In addition to ACKs from the other side, I'm also getting packets that are coming back my direction, and vice versa. So there's two different sets of sequence numbers. We're not going into that. We're just talking about one-way communication right now, okay? Now, this 100, by the way, again, it's a random 32-bit number, so and that's done to avoid a whole bunch of security holes, which we could talk about another time. But anyway, so here's an example of a packet with some data that's coming in at sequence number 100. It starts at 100. It's got size 40. So notice that the fact that 40 bytes came in and they were successfully received means that we're now up to sequence number 140. Because we've received 40 bytes more than sequence number 100. And so what we give back as the ACK to the other side is, hey, we're at sequence number 140, and my buffer now only has 260 bytes worth of space. So notice in the question earlier, how does the sender know what's available? There it is. Okay, it's in the header. Now, here comes another one. This works fine. Okay, nothing too exciting. This one is an interesting one here because notice that this packet says, here's some data from sequence number 230, and its size is 30, but when the receiver goes and tries to put it in the buffer, it says, oh, there's some bytes missing. Okay, so you could imagine that there was some lost bytes somewhere along the way. And notice that the acknowledgement here is kind of an interesting one. It says, hey, I've received up to 190, and there's 210 bytes in my buffer. So notice that this is the same. Why? Because it's only received continuously up to 190. Okay, it's not going to acknowledge 260 because that would implicitly say that everything prior to 260 has been received, but we got a hole. Everybody with me on that? Yes.
Is this only true for using individual acts? Like, does it change if you're using full information acts or something different?
So there is another type of acknowledgement which can tell you where the holes are, but the basic TCP protocol is a I've received up to protocol. Okay. There's something called selective acting, and that's in the options of the TCP header, and it has to be negotiated on both sides, and so it doesn't always work. But so this is the basic TCP protocol. So notice again, we only ACK up to 190 because we haven't received some bytes. And by the way, notice that the ACKing here is low overhead. It's very simple. It's just a 32-bit number telling us kind of how much we've received up to and how much is available in the window. So this is a very small part of the header. So the TCP packet coming back toward me is mostly about the data coming toward me, but it's also telling me about the ACKs at the same time. Now here we go, we're continuing. So the next thing we receive, so we're receiving this and we're buffering it, but notice that we're in trouble here because we're only ACKing up to 190. And at some point, the TCP stack on the sender side says, oh, wait a minute, something's wrong here. I'm only ACKing up to 190. I'm going to retransmit a missing packet, which fills this in, and the fact that it filled it in, all of a sudden now we're ACKing up to 340. Okay, because now we've got it all. Okay, and so then we don't have to retransmit anything else, and we're good to go. All right. And notice how, by the way, the buffer went to 0. So what's good about this is if I've got a connection stream and the receiving application is just too slow and it's not doing anything and it's stopped, then what this automatically does is it tells the sender, stop sending anything more because I can't receive it. Okay? And so the way this remaining buffer space works is it allows us to try to send as much as we can, but we know we'll never send more than the receiver can receive. Okay, now I'll talk about congestion avoidance in a moment, which is the flip side, which is we also don't want to send more than the network can take. And so we might send less than the receiver can receive if we want to be a good citizen. Okay, questions? Yes?
Why is it that before the retransmission or finally got up to 340, why doesn't the amount of space that you have buffer stays the same? Couldn't you then overflow it? It stays at 192.
Because this is saying I've only received up to 190, and after 190 there's 210 bytes worth of space. So in principle, you could keep retransmitting pieces of this in different sizes. You could do whatever you want. It could say on retransmit, it could say 190 and give you 100 bytes in that packet if it wanted to, and they would just get overwritten what was already there, and then at that point you'd get an ACK saying, I got everything. But the point is you interpret this number relative to the sequence number. It's a good question, though. Okay, yeah. Then you can't do that. So you can never send more than would fit in the window at the receiver side. Because you always know, looking at this, you know exactly how much you could send, and you know what sequence number you're up to. And so you actually have enough information here to never send more than the receiver can take. Now, the interesting thing that we haven't discussed here is two adaptive things. And again, I'm not going to go into this too much longer because I don't want to dwell on networking more. But you can adapt at the window size at the receiver, because if the receiver's got too little window, then maybe there's no way for the sender to get enough to fill up the network. And the second thing is you want to adapt the sender to be a good citizen. Okay, so those are two things you want to do. Question, go for it.
So when the initial window size is being created, like let's say you have like a user and a server that are trying to communicate, and the server sets the window size for the user, does the server adjust like the window size for current connections when other connections are added?
You know, typically that varies a lot depending on the stack. The simple thing is that there is you've set a parameter as to how much window size you want to allow, because it's, you know, basically however many connections you've got, you want to make sure, or the max number of connections you can have, you want to make sure you have enough window space for all of them. You could, in principle, adjust that, that does happen on some of them, but it's not as common. The thing that adapts a lot is the window on the sender side. That's the one you're thinking of, maybe. The receiver's window is even a compile option in some older kernels as to what it is. Yeah. So how do we deal with being good citizens? So the question is sort of, number one, how long should the timeout be for resending? If it's too long, we waste time if the message is lost, and if it's too short, we're wasting a lot of stuff even though the ACK is about to arrive. There's a stability problem. If I send too much stuff, the congestion will cause packet loss, and then I'll have more ACKs and more stuff, more missed ACKs and more stuff I have to send. So if you send too much, you actually lose more. Okay, so there's a downside to congestion. If you send too much and you send it too fast, it'll start dropping more packets, and then I'll have to retransmit more, which will cause more congestion. So you got to get this right. All right, and you take a class on networking, and they'll talk a lot more about this. But basically, the sender's window size has to be less than the receiver's buffer size. You try to match the rate of sending packets with the rate that slowest link can accommodate. And there's an adaptive algorithm whose goal is fill all the network between the sender and receiver, being good citizen about it. And basically what you do is you slowly increase the amount you have outstanding until you start losing packets, and then you back off. Okay, it's called slow start. There's many following options because this one tends to over-adapt. But notice what happens if there's no timeout. We keep increasing the window size by 1 for each ACK. And then when there is a timeout, we cut the window size in half. So this is called additive increase, multiplicative decrease. And if you ever look, those of you that have taken networking classes or whatever, if you look at the profile of transmission of a TCP stream, you'll see that what happens is it rises up and then it goes down and it does this. It's a sawtooth. And that's exactly this. Okay. All right. Any questions on this? Because then we're going to leave this. Now that we have working, reliable connections, we're about to use them for something. Okay. Good. So, let's now pop up a level again. So, let's suppose we've got a big network with a bunch of storage servers, and we want to build distributed storage. And the reason we might be interested in this is really packets are almost blasé and boring. What's really important is the data. It's all about the data. And so we can ask a question, if we're going to build a system where the cyberspace keeps all of our data, how can we do that? Okay? And that's often called network attached storage, but there's something called the CAP theorem, not about this kind of cap. Okay? Consistency, which is changes appear to everyone in the same order. Availability, you can get the result at any time. And partition tolerance, which says even if I chop apart part of this network, I can continue to get good results out. So that's consistency, availability, partition tolerance, CAP. And the CAP theorem says you can't have all three at the same time. You got only 2 or more. More is not possible, 2 or less. Okay, so you could get availability and partition tolerance. You could get consistency and availability, or you could get consistency and partition tolerance, but never all 3. And this is also known as Brewer's theorem for Eric Brewer, who postulated this back in the early 2000s. And it was kind of a hypothesis for the longest time, but it's clearly been shown to be true if you're very careful about your specifications of what these mean. And then there was a whole issue to a distributed systems magazine. Oops, are we about to lose our... Nope. Hello? There's a distributed systems magazine that basically did CAP theory proofs by lots of theorists throughout the country and world at one point, proving Eric's theorem, basically. So this is the CAP theorem. Are there any questions on this? Can't have all 3. Only 2. So perhaps this, let's give an example here just to think about this for a moment. Let's say we have availability and consistency. That means it's always available and it always gives me consistent results. Think about what happens when it gets partitioned. What happens is, I can no longer be available because in order to be consistent, I got to talk to every copy, but it's partitioned, and some of those copies are not available to me anymore because they're on the other side of a broken network. And so that's why, for instance, you can have consistency and availability, but not partition tolerance at the same time. Okay? This is one of these laws of the universe that's unfortunately very hard to violate. And when you're designing a distributed system, you should always think about the CAP theorem and understand kind of what you think you're getting for your semantics. Because if you think you're getting all 3, then you might be fooling yourself. All right. So Any other questions on that? Yes? Say again? So how can you have consistency and partition tolerance? Well, what happens is, what it says is my system will keep working even when the network is partitioned. It'll work properly, but it stops being available. So it works okay when the network partitions, and it's always consistent. But when there's a network partition, then, for instance, my writes will no longer work properly because they can't get across the partition. So you get C and P without A in that instance. Because when I don't know if does that make sense? So when it's partitioned, it can't be available anymore because you can no longer deal with not being able to talk to all of your copies. All right? Good. Okay. You want me to do A and P? So the system can be available and partition tolerant if you got a zillion copies, and when they're when you get a partition in the network, you just talk to a local one. You may read and write the local one. Now, there's other copies on the other side of the partition that are getting very inconsistent with you, but boy, you're still available, and boy, you can deal with partitions. Okay? You could argue whether that's a useful scenario or not, but yeah, A and P without C works as well. Okay, so let's talk a little bit about what a distributed file system is. So the simplest thing is you have a client or clients trying to read a file from a remote server and getting data back over the network. That's why it's distributed. So it's transparent access to files stored on a remote disk. And let's start by very quickly asking about naming. So you could, for instance, name every file by giving the host name of the server and a local name to mount every file and talk about it, okay? And so this is an explicit naming of the files, but of course there's no location or migration transparency, so this might be not that desirable, okay, because you might want to not name this by its explicit host name. The other option, which is more common, is mounting. So the idea here is I'm taking, like COEUS, and say mounting a home directory on my local root system. And so what happened there is I have /users/su is actually the root of some remote file system. So when I say /users/su/foo, that's really /su/foo on that remote COEUS server. And the naming system of Unix, for instance, will automatically, after you've mounted this remote file system, it'll now let you use names like /users/su/foo, and it will automatically redirect your queries to that remote file system. Okay, and that's probably something you're very familiar with and have probably been using without even knowing. The last one is a single global namespace where every file in the world has a unique name. Okay, and this is actually a pretty cool option here, right? This is one where the name metadata is hashed. We'll talk more about that next time. And as a result, there's a single name no matter where you are in the world, and it doesn't matter what file server it's on, you just have access to that data. That's a little different than this mounting thing, but it is kind of where we're starting to go with cloud storage, where kind of every file is accessible anywhere and has a unique name. Okay. So we're going to talk really quickly of simple distributed file system, and then we're going to take a break. So if you think about a single distributed file system, we've got clients are doing reads and writes. When we do a read, we're getting data. When we do a write, we're getting an ACK. The remote disk has reads and writes forwarded to the server. This is the simplest idea. And you use remote procedure calls to talk to it. So typical systems actually use an RPC like Sun RPC. There's no caching on the clients, and the server might use a cache. And so the advantage is this is extremely simple. You guys could probably build one of these today yourselves, where you have a server software you put together, and your client is doing read and write system calls using RPC to that server. Okay, that's actually within your grasp of something you could do. The problems with this is very bad from a performance standpoint because there's no caching on the clients and you're always going over the network for every operation. Okay? So let's take a break, and then I want to talk about caching, and then we're going to move on to some bigger distributed systems. Let's do something with this now. So one thing we can do to reduce network load is give caching in here. So let's put caches in the system. Here we go. Okay? So the advantage is if you open, read, write, close, you could do it entirely locally without ever going over the network. Okay? Doesn't that sound great? Problems are failure. The client caches may have data in it that hasn't gotten back to the server, and so if the client fails, you lose your data. Another problem could be cache consistency. What happens if the client caches aren't consistent with the server or with each other? Maybe you get the wrong results. All right? So for instance, here I'm reading. I do my read RPC. It gets cached in the local file system buffer cache, which you guys are all doing for Project 3. It comes back with data. The data gets put into this cache, and I get a V1 back. And notice how fast my reads are. So that's great. Meanwhile, this guy does a write. He's going to write version 2 of that data. It crashes, and now the reads maybe don't give us any data back. That's version 2 was lost. Or we have a situation where the data was updated, but crashes, and now in this situation, the server cache has the data, but this client cache still keeps returning the old data. So we've got some issues here, right? We got to make sure that writers' data gets propagated to people that care, and we got to make sure that writers' data makes it to the file server in order to make sure it's permanent. Otherwise, we could lose our data. Okay, so caches are great on the one hand, but can cause problems on the other. And so what might we want to do? Well, what if the server caches Can the client wait until the server comes back up and continue as before? Maybe. Data in the server memory but not on the disk could be lost. We have these RPC states. What if the server crashes after we do a seek? That could be a problem. We might retry our messages. Suppose the server crashes after it does a remove but before an acknowledgement. We keep retrying, except the second time we retry, there's a failure. So there's a lot of things about this protocol we have to be careful about if the server fails. So one simple idea to make all of this simpler is a stateless protocol, which is a protocol in which all information required to process a request is passed with the request. And so there's no shared state between the client and the server. Okay? So if the server crashes and restarts, the request can continue and there's no problem. So think about that for a second. This is a situation where normally if I open a connection, I have an open file handle, that's state. If the server crashes, now the server comes back up, it doesn't know that I opened the file. Okay, so a stateless protocol would somehow work in a way that would allow me to not have that shared state. Okay, and in fact, that's good, right? What if the client crashes? Well, I might lose some modified client data, but basically other things that other clients might continue. So network file system, how many people have used NFS before? Probably all of you don't realize it. This is a Unix file system that's been around for a long time, since the 80s. Originally by Sun Microsystems. It has a Unix file system interface, open, read, write, close. It's got a special layer under the covers. I'll mention something about that in a second, called the VFS layer, which allows the same operating system open-close interface you're used to work both for the local file system and for the remote file system. Okay? The protocol is an RPC using that XDR IDL layer that I told you about that can deal with the fact that certain servers and clients might have different endianness or different codings. And it has write-through caching. So this takes care of that first failure I talked about where the client writes something into their cache and then crashes. NFS, in the simple version, requires all writes to go all the way to the server for consistency. Okay. The interesting thing about NFS, other than it being very popular, is servers are stateless. So I don't have to open a file for NFS at the operating system level. What happens is all the communication between the client and the server does something like, rather than keeping track of where you are in the file, every read says, well, file I number, position X is where I want you to read. So explicitly encoded in every message is the position you currently are in the file, so there doesn't have to be any shared state. And there's no open or close, okay, because NFS basically allows you to just start working on any given file automatically, and the operating system gives you the illusion of the open and close at the client level. So it's totally stateless. And that means every operation's idempotent. So performing requests multiple times has the same effect as performing it exactly once. So examples, the server crashes between disk I/O and message send. Well, the client just resends it. Read and write file blocks. You just reread or rewrite the block. The same thing happens over and over again without changing anything. The one that's a little tricky is if you do a remove, NFS does the operation twice, and the second time it returns an advisory error. But this is mostly under the covers, so you don't see this. The failure model is supposed to be transparent to the client, where the server goes down, comes back up, you never notice. Okay, except you can, because it's possible that your system just hangs and never comes back up. So that particular failure model is often one that is explicitly disabled because it's a problem. Okay, let's talk about cache consistency. NFS protocol versions 1 through 2 and or 3 is weak consistency. The client polls periodically to see if anything's changed. Poll the server if the data hasn't been checked in the last 3 to 30 seconds. And that's when a file is changed on one client, the server is notified, but other clients eventually find out. So if you look, here's a situation where we have a client that has an old value in its cache, and there's a new value that's made its way to the server. And what happens is every now and then, like every 3 to 30 seconds, we get a poll saying, has F1 changed? No, it's not okay. Here's a change. Update. And at that point, the read will give us the right value. So what's interesting about this protocol is, one, it's eventually consistent. Okay? I used to use the early versions of NFS a lot, and I'd have a window open on a server, plus I'd be editing on my local machine, and you could get in a situation where you'd edit some data, and then you'd go to compile, but the compiler would get the slightly out-of-date version. It was very weird. Okay? NFS has been putting some more fixes in over time to make that more consistent. But okay, I'm going to tell you about another option. Okay, I'm going to skip this. I want to say something about the Andrew file system, which is a different option. So the Andrew file system came from CMU in the late 80s, and it has a different idea. Rather than this polling consistency, it's got a callback. So if the server finds out that somebody changed data, it'll actually send an invalidation to everybody who's sharing that data and tell them there's a change. Okay? And the other option, which is very interesting, is when you modify data, it only becomes visible when you close the file. Okay? And so this gives you much cleaner semantics and much more scalable. So in AFS, everyone who has the file open sees the old version until they close the file and reopen it, then they see the new versions. So you always get consistency. Okay. All right, I want to skip this. Let me just say the implementation of NFS. Actually, so the nice thing about the Andrew file system is this idea of consistency, which is only on close do updates show up. This is much more scalable. Okay? And whenever you do close and the data gets updated, then the caches of everybody who's sharing do get invalidated. So that's good. Okay, so if you look at the implementation of NFS, basically at the client, we have read-write open. We go through something called the VFS layer, okay, which then allows me to connect a bunch of different things together, like the local Unix file system or NFS. And so the difference between whether I go over the network or not is purely whether it's a local file system or not. VFS hides that detail, so the user doesn't have to know. So you could mount an NFS file system in a local root system, and it just works. That's what I showed you earlier. Okay, and that's all because the VFS layer is hiding the details. And so the VFS layer will automatically redirect to the NFS client if there's NFS partition, which goes down, does the RPC across the network to the server, back through the VFS interface on that side and the local file system, and that's kind of how NFS works. Okay. And so the cool thing about VFS is I can have all sorts of file systems tied together. Okay. Now, I don't want to do this because we're low on time. I do want to do this, though. So as our last little topic, let's talk about how to handle huge volumes of data. So we've talked about NFS and local file storage and local area network file storage. But suppose we've got petabytes of data. What are we going to do? So what we might want to do is change our interface, because the file interface is tricky to scale to really large global scale storage systems. So let's do something simpler. Let's talk about a hash table interface which has a key and a value. And what the interface is to write, you say put, here's the key, here's its value. And what you ask for get, you say here's the key, tell me what the value was. So this distributed hash table interface is a very simple interface that perhaps we can do much better job of scaling for very large systems. And sometimes you could think of this as a simpler but more scalable database. So how many people have run into distributed hash tables before? Anybody? How many people recognize this simple interface as a regular hash table? This looks like a hash table, right? Put, key value, get key. So what we're going to do is we're going to follow after a whole bunch of companies like Amazon and Facebook and iCloud that have all decided that key value stores are very scalable ways to put zillions of petabytes of data on the network. And in real life, Amazon's got the DynamoDB, which is an internal key value store used to power Amazon.com shopping cart. There's a bunch of distributed scalable data storage from Google, like Bigtable, HBase, Hypertable. Cassandra is what Facebook came up with. Memcached is an in-memory key value store. There's eDonkey and eMule are peer-to-peer file sharing systems. All of these things present distributed hash table interfaces. So clearly people have decided this is useful. So what's a distributed hash table? Well, it's something very simple. Main idea, you partition all the possible keys across many machines. And so certain ranges of the key space come up on different machines. And so when I want to build my distributed hash table, all of my queries have to go through some sort of directory lookup to figure out which machine to query for, and that'll give me my data. Okay? Now, what are some challenges? One is, what happens if all of my keys in a certain range are on a given machine and it fails? That sounds like I got to deal with it somehow, right? Scalability. How do I deal with thousands of machines? So it seems like perhaps the simple centralized directory might not be a good idea. How do I deal with consistency? So I want to maintain data consistency in the face of node failures and message losses. What do I do? How do I deal with lots of different network speeds? Okay, there's many challenges. So some questions are, in the put key value, where do you store the new key value tuple? And in the get, where's the data? So, and how do I do all the above by getting fault tolerance, scalability, consistency? Now, we can build a directory like this, have one machine store all the mappings, and so when I do a put, I go to the master directory machine, it looks up where key 14 is, and it says, oh, I don't know where it is, but I'm going to allocate a node for it. Key 14 is henceforth going to be on node 3, and then it can put the data on node 3 and give me back an ACK, and I'm good to go. Now, when I go to get it, now this time I can look it up, get the value, get it back, and go. This is a very simple key value store. Okay? Seems like it may have some scalability issues, like how do I make that directory work well under high load? Right? What are some options here on how we can do this? So we were just showing you what's called a recursive query, where if you look, we have the request is actually routed to the node and back. So, for instance, we could do something called iterative, where when we put, the result comes back with where to put it, and I, as a client, go ahead and put it. Okay, that's called an iterative. Oops. This is an iterative way of doing things. Notice that we put less load on the master, but we're requiring the client to do all the work, and this is potentially slower. And the same thing works with getting values where I find out where the data is and I get it back. So that's the iterative and recursive option. The difference between these two, the recursive query is faster, but it may have scalability bottlenecks as all values go through the master directory. The iterative query scales a lot more, but it's potentially slower and it's much harder to enforce consistency. I'm only telling you about these two options because they're interchangeable in the way people use them to implement. Okay. So what about fault tolerance? Well, now, rather than storing the data on only one thing, I'm going to store it on multiple nodes. Okay? Obviously. The way you get fault tolerance is you put more than one copy. Okay? And we can do this as iterative or recursive. These are all different possible options there. Okay? Question? Yeah. So an interesting point there is that a misbehaving client could cause inconsistent data. Yes. However, However, whatever access control mechanism you've got in the master directory can also be enforced by the individual client. So if you came up with an access control scheme that would enforce consistency, you could enforce it even in the iterative case. But it is a little trickier in the iterative case to get full consistency because you could get different values written. That's true. Unfortunately, the other way to answer your question here, though, is also with failure, you get inconsistency anyway. So inconsistency is kind of like the name of the game in these kind of systems, because if you got two writers at the same time. Okay, so how do we get scalability? We use more nodes. We could serve more requests from all nodes, which the value has in parallel. So these are like RAID. Okay, so we basically just come up with a scalable RAID. How do we make the master directory scalable? Well, that's a little trickier, but maybe we replicate it or partition it or whatever. Seems like there are options. How do we do this? Well, we also have to ask, what do we do when we add a new node? Okay, so I'm not going to be able to say what I wanted to say here today. I'll have to finish this up next time. So let's talk a little bit about load balancing. So the directory keeps track of the storage availability at each node. And when you add a new node, potentially you have to redistribute everything to get load balancing. And how do we do that? I mean, nothing I've told you so far tells you about rearranging things to deal with load. And in particular, what happens if, some key is really popular and that basically nodes 1 and 3 are way overloaded. And as a result, the rest of the nodes are not doing anything, but 1 and 3 are overloaded. What can the directory do? Well, maybe it could rearrange some of our data to take load off of these 3 or these 2 nodes to do something, but we haven't really specified how to do that. So we got to worry about things like that. What happens when a node fails? You need to replicate values. So there are lots of questions here. And there's a lot of potential consistency questions. And I think we're going to need to pick this up next time. But what I wanted to, let's do this next time. I did want to show you a little bit about consistency issues here. So let's do this next time because I don't want to shortchange this. So we've been talking about distributed file systems, which are transparent access to files stored on a remote disk, caching for performance. We talked a bit about the virtual file system layer, providing mechanisms so that you can have the same system calls for different file systems. And we started talking about consistency, keeping client caches consistent with one another. And if multiple clients, some are reading and some are writing, what happens to the consistency? NFS checks periodically, AFS registers callbacks. All right, let's pick this up next time because I think there's some, I want to talk about CORD and other distributed hash table algorithms in more detail. So you guys have a great weekend. Please come on Tuesday. We will finish this up with some good information about security, and we will then have an exam on Thursday. See ya.